Yeah, I think you can start.
Sounds good. Yeah, you can see my screen, right?
Yeah, right.
Okay. Great. So this is some work that I did a few years ago and have just revisited again. Um, I guess I just want to say, first of all, I'm excited to meet others in the region, uh, in like this Paleoglacier working group. Even though I've been more focused on modern day glaciers, it's um, really fun to hear the other talks and meet other individuals. So yeah, I'm happy to be here. Thanks for inviting me. I'm going to talk a little bit about debris cover evolution and a remote sensing problem that I worked on and am still trying to get back to. Um, and some of the future work I'm hoping to do with that. And I wanted to start off just with a disclaimer, since this is a Paleoglacier working group, that I'll be talking about modern glaciers. And so far, I've listened to many of the talks, and they've been really fun, involving field work and collecting samples, and like beryllium 10 dating and whatnot. But all of this work is remote work, and I ended up doing this um, as a backup plan since my um, really the pandemic caused a few things to shift, and so it's really nice to be able to fall back onto to work with just remote sensing imagery. And this allowed me to finish up a final chapter and yeah, and move on and start teaching. With that, I'm actually involved in a lot of snow projects right now, and so it's fun for me to start thinking again about glaciers. And I've been talking to some other local folks. I think I saw Matthew Morris on the call today, and I don't know, maybe Leif Anderson is also here. I've been talking with them, and they've been including me in some of their conversations. So I'm hoping to do some interesting rock glacier work with them. Um, but yeah, I figured it would be fun to show y'all some pictures that I took just this past winter, so just a couple months ago. We did go down and backpack around in Patagonia, and here's a picture just below the Glacier Torre, and you can see just these series of moraines. So I guess it was all meant to be. I was already getting excited about these glacier moraines, and my wife was had enough of me talking about it and looking up information in the area. So it's definitely time for me to start thinking more about glaciers, and I think maybe paleo glaciers as well. What I'm really going to be talking about today is work in high mountain Asia, and I'll be focusing more so on the greater Himalaya. This area, I'm sure many of you are aware, is a really critical area, since it's the water towers for nearly 2 billion people living downstream, huge socioeconomic impacts, disputed country borders, and I was able to work with several other brilliant scientists, trying to understand how much water we have in this region and how it's going to change over over the coming century, what that means for everyone in this area. Um, in this area, dubbed as the third pole, I'm sure all of you are pretty familiar with this area. And the water budget consists partially of snow cover and very heavily glaciated. Some of these rivers, the summertime meltwater contribution can be up to 60% coming from these glaciers. And so it's really critical and important to understand how they're going to evolve and change over time. There have been some really interesting, so a lot of interesting remote sensing work done in the area to look at mass loss and mass balance. So here is a paper from Sheen et al. That was quite a large study over all of high mountain Asia, looking at that mass balance. And you can see along the greater Himalayan arc, this is an area where glaciers are losing mass more quickly than other parts of this area. And one characteristic of this area, it's really rugged terrain. So here's this oblique image from hexagon imagery from Josh Maurer. And you can really see that this area has a lot of steep topography, which produces a lot of rockfall and debris accumulating on many of these glaciers. And there have already been some different studies that have estimated the amount of debris cover in these areas to be pretty significant compared to other places worldwide. And I'm sure many of you are familiar with the evolution of debris cover. Essentially, a lot of this rock fall gets entrained in the ice and makes its way through as it reaches into the ablation zone. It's exhumed and arrives on the surface. Under a warming climate, your ablation area continues to expand, and that debris cover can continue to grow. And many people have been looking into this. It's a hot topic, since understanding this problem is really critical for fully modeling all of the different glacier types that we see in this area. So many have looked at individual glaciers or glacier basins and observed satellite imagery and looked at a change over time. So the figure on the left is from Capano, or however you pronounce that. And they used this along with some modeling to get an idea of how debris cover was going to expand in the coming century. And there's this paper that I'll refer to again, this Heride and Pellicati. They did a large debris cover analysis globally. And really, I guess it's a little bit controversial, not this paper, but just the idea of how glaciers are going to change over the next century. And, there's this schematic here where they have these different stages of this glacier, where it reaches its maximum carrying capacity for debris cover, and then it eventually detaches, and there's not a lot of internal deformation, becomes more of a rock glacier. But even that is still disputed among some people. They're not totally sure how it's going to play out. But in general, they do see that many glaciers kind of follow these different stages, both in high mountain Asia and throughout the world. And this, I'll refer back to this because they created a very useful glacier inventory, and I use it for validation. And let me go through this a little bit faster. I feel like I'm taking too much time talking about the basics. Basically, I'm interested in understanding how this debris cover evolution, and it really hasn't been observed systematically, and what I started thinking about was, it would be really nice if we had a fully automated, scalable way of assessing debris cover gain from satellite imagery. And so I kind of shifted towards a remote sensing focus and diving into these different remote sensing techniques. And so it's definitely a lot of focus on the methods in this area, and some immediate challenges that you run into trying to do this in a way that's fully automated, that doesn't require any training. And I know there are some great models out there, machine learning models and deep learning methods to classify debris cover, which are really great. But I went for a more simplistic approach that didn't require any prior knowledge. And so some challenges in this area: a lot of cloud covers, and even just selecting the imagery is very time consuming. All past studies that I mentioned, they use manual intervention. they neglect and throw away a large amount of imagery and just choose cloud-free imagery because it's easier to work with. Furthermore, this area has this steep topography, which introduces large shadows and frequent summertime snow cover. So yeah, basically find an automated approach, but that required diving a little bit more into these remote sensing methods to detect this change in debris cover. I'm sure you're all familiar with Landsat, and I just focused on Landsat only for this study. I chose 5 different tile locations spanning the greater Himalaya and Karakoram region that all contain a significant number of glaciers and glacier area. And I used the Randolph Glacier inventory to help with this. So this is not classifying the glacier areas. I'm relying on existing data and really just focusing on a change in debris cover, which I realize over time is going to introduce some errors in glaciers that are retreating. Just thinking about that first problem with cloud cover, now some of these areas at the end of the season can have more than 75% of the image covered by clouds. This is over a 20-year time period, looking at Landsat, and you can see particularly in areas influenced by the summer monsoon, which is more so in the eastern side. I should have flipped this graph around because Bhutan and Everest more on the east side, and then Karakoram on the west. You can really see that influence from the monsoon. And so a large amount of the imagery is just thrown away, and that can be problematic if you're trying to capture the scene with the least amount of snow cover that is most representative of debris in that area. So I set up an approach that first just includes a classification using some simple band ratio methods. Also looking at some thermal information using a glacier inventory, and I created something that deals with shadows that I'll talk about in a minute, just to help us understand where snow and ice exists and where debris cover exists. I do this over several scenes for a single time period and combine that information, and then compare that to another time period to observe the change between these two times. So I'll walk through that a little bit. The classification is kind of straightforward, though I spent a lot of time looking at clouds for being interested in glaciers. It's surprising how much time you are just looking at other things. So I combined 2 different methods for separating snow and ice, both this NDSI and ratio method, and used a cloud mask. And I relied just on the built-in cloud mask, which ends up having some problems, which I'll talk about in a minute. One part that I spent a lot of time on is trying to account for these shadows. So here you can see these large shadows cast in this area, and in a classification like this, those are going to be often erroneously classified, which is an issue that Scherler and Haridin-Pellicati and others discussed quite a bit. But I implemented this basically a ray tracing algorithm that uses the NASA DEM with the Landsat imagery to project where shadows are going to be. And there are artifacts within the DEM, and so it doesn't do a perfect job. And so I use this dilation where I expand out from that area and do a little Gaussian like mixture analysis where I look at distributions that are probably shaded pixels, which is this red distribution. And then there's a second distribution that is usually areas that are in shadow, but there's a cloud covering them at the moment. And so with that, we're able to, just use solar geometry at the time of acquisition we can determine where shadows are, we dilate out, and yeah, can really carefully mask out shadows. So that spent a lot of time. Again, it's kind of a funny thing, you know, it's like I'm interested in glaciers. I ended up looking at clouds and shadows um, for the most part. This is kind of the final image for, this is the Everest region in the bottom right, and it's just zoomed in on part of this tile. In the center is the Nagazumpa Glacier, which is studied quite a bit for its debris cover. And on the right, in that bottom right, you can see the Khumbu Glacier. And it just shows areas over this full time period of Landsat Oli where snow and ice have persisted, debris have persisted, and a gain in debris, and in some areas, a gain in snow and ice, but that's usually an error. Without getting too far into it, since I maybe spent a little too much time at the beginning, the cloud masking has some problems where if you just rely on the cloud mask, you end up fully excluding most of well, a lot of the debris covered part of a glacier, which was kind of a concerning and surprising thing that we found with some of the crevasses and ice cliffs and supraglacial lakes. It ends up mixing the signal, and you frequently have the Landsat cloud mask picking up these the debris cover on the glacier, and so it would just throw out the image. So I have to adjust it by finding areas that it says are 100% cloudy all of the time during this end of, we kind of just focused on the end of the kind of end of the summer ablation, minimal snow cover time period. So the main part of it is while I'm looking at this debris cover classification over 2 time periods, I also incorporate the thermal imagery, which isn't perfect, but used in conjunction with the classification and combining the two together helps us get a little bit closer to, or just have a little more confidence that we are looking at an area that has changed. So this final image that I'm showing here, that's just between time 1 and time 2, it's both a optical classification from those band ratios and masking and everything, and looking at thermal differences over this time period. And it's really using as much imagery as it can. And that's kind of the point that I had in mind. So to validate this, I used this other data set that was built over a long period of time with manual selection and masking to see how it holds up. And it's difficult to validate because I had to focus on the year when they acquired their image to see if my model ended up doing a good job at estimating what they considered to be debris and ice. And it's a little bit different. Part of that is partially because they use the ratio method while I use the ratio and this NDSI method. And so I definitely need to look into it more. And there's some other areas that you can see here as well with some of the superglacial lakes. But in general, we're capturing the main signal here. It's just some fine tuning. For most of the regions, it's high. Now, some areas like the Himachal Pradesh, like recall is pretty low in the precision metrics. And a big part of that is actually, after investigating, due to dust loading and how dirty the glaciers get in that area. So you can see it does a really poor job in the classification to the right. But really, these performance metrics are all just looking at one single year that align with the acquisition season for that Haridem and Peleoglaciers study. Whereas the actual results that I present, I use at least 2 years, and you can see that it does quite a bit better the more imagery that it has. And again, not totally perfect, and this is still kind of a work in progress. Furthermore, we found that some areas maybe had some big mistakes in the Horide and Peleoclates study, which, yeah, we are not so sure what's going on there. And these are the main results. So in general, over all of these 5 regions, there's a debris gain of just over 1% over this 7-year time period. So it's a really short time period. And you can see in this subplot here, most of that debris cover gain is right where you would expect in the lower elevations. The line right here is showing median elevation of these glaciers in each of these areas. And yeah, that's quite a significant change for such a short time period. And the main goal is to take this data, and there are some really smart folks that are interested in validating their modeling, and that's really the end goal. We want to be able to model how debris cover is evolving over time and how it's going to continue to evolve over the coming century. And so here I'm just showing this mean vertical ice flux. So it's just DHDT from the Sheen et al. Paper for ice, debris, and debris gain along elevation up here at the top. So you can see the elevations that experienced the greatest change in debris gain. And then also along slope, this line here is 10 degrees, and you can see again, where most of this gain in debris is happening. I realize there are some issues with this since it's just this vertical ice flux. Really, we would want to see an integrated ice flux to really understand how debris is evolving over time. Yeah, so there are some promising results, but it definitely needs a bit of work. And yeah, we're going to try and improve on that a little bit, and yeah, explore that a little bit further, since it ended up being quite a methods exploration. And now I'm honestly just very busy teaching and doing many other projects. It'll be fun, and I think this has been a good opportunity for me to jump back in and start thinking about this, and maybe I can make some connections with people that would have some great tips and great advice for this. But thanks for listening.
Great talk. Do we have any questions? I think we can have 2 questions. Okay, Yue.
Um, I have 2 questions, but I guess I'll ask one first. I'm wondering, are there any correlation between debris cover and the debris flux? I'm thinking like if you know the coverage of the debris in a certain area on a glacier, could you infer somehow like how much debris is actually like volume-wise in the glacier and how much like 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 volume debris versus volume ice in the area. Is there a way to estimate that?
Yeah, I think actually Leif Anderson has looked at that a little bit. So it's hard because you need to know the thickness of debris for all of these glaciers, which that's extremely hard. We only have a little bit of data for that on a few glaciers. And it's really easy to get that spatial coverage. So that part's not so hard. And then a lot of the modeling that others are doing, they're looking at sort of that accumulation of debris. And part of that has to do with the slope of these glaciers. And as you are accumulating a lot of debris, this is down at lower elevations, and it's you just need to think about the ice dynamics. And the hard thing to think about is, well, how much is actually getting entrained, and modeling how much debris is falling from this catchment into the ice and then traveling through. It's such a complex problem. And so yeah, this is just one little part trying to say, well, can we provide some observations that maybe help us understand or inform those models a little bit more. And that's what I hope to do with this, but it still needs some work for sure. Thanks for the question.
Thank you.
Any other questions? I think earlier you have some question.
No, sorry, that was just a clap. Thanks for the talk though, Matt.
Thanks.
Okay. So I think we need to move on, but I think after we finish the second talk, if you have more questions, we can continue to discuss.
Yeah, sounds good.
Very interesting talk. Our second speaker is Yanan Nancy Li. She's the assistant professor in Department of Geography and Environmental Study at Texas State University. She graduated from University of Tennessee, have a master and PhD here, and then focus on dendrochronology during her master study, and then moved to glacial geomorphology, cosmogenic, and spatial analysis during her PhD work. She worked at South Dakota State University for 2 years, and then moved to Texas State in 2018. So she's a mother of a 3 year daughter right now, and then currently we'll have another baby in about 2 months. Okay, right now I will turn this to Nancy.
Okay, I believe I'm sharing the right screen. Yeah, all right. Okay, let me get started. Thank you so much, Dr. Lee, for that nice introduction. What a coincidence. I didn't know Matt is expecting a baby in May. I'm expecting a baby here too in May. Well, just so bear with me if my brain doesn't work fast. So I feel very honored to be here to talk to this Paleoglacier working group. Thanks to Ben for organizing this since last year. It was very nice, and it makes me feel belonging here since the participation of last year. But anyway, thank you. I feel very happy to be here and feel humbled to give this talk on Little Ice Age glacial moraine dating in High Mountain Asia. So happy to be in the same group with another High Mountain Asia talk. Yes, as Dr. Lee said, I'm an assistant professor at Texas State University. And I want to just point out to this background photo that I took about 4 years before pandemic during one of my field seasons. This is in central part of Tian Shan, northwest in China. And this is just a gorgeous place to study geology, geomorphology, all the natural processes. As you can see, a lot of features you can just talk stories about, right? The terraces. This, where my mouse is the fresh deposited Little Ice Age moraine that I'm going to lead you to. Yeah, so here, the topics on High Mountain Asia. So as Matt has introduced us, this is the crucial region that encompasses the Tibetan Plateau and the surrounding mountain ranges, including the Himalayas, Karakoram, Hindu Kush, Pamir, and the Tian Shan to the north. It has the largest volume of ice outside of the polar caps. So it has the nickname of the third pole. So it has this very extensive thickness in various sectors listed over here, such as infrastructure, pasture flooding, agriculture, glacier lake outburst flooding, debris flows, and tourism. So this is important for that many people living in the place and in the downstream locations. So change of the climate change effects will impose a big consequences on those people living in the region, and also speaking to this especially vulnerable and high altitude environment, studying glacier and snow, all the cryospheric changes is key. So this is the topographic, the digital elevation model of the region in general. So you can see those white color is indicating the extensive ice and snow in the region. So just say, there are quite amount of mountain ranges in the region. Sometimes the border between one range to another is hard to separate, but these are high mountains up to 8,000, more than 8,000 meters above sea level. So I have two stars on the map. One is the red colored star in Tian Shan. That's one of the focus that I'm going to be talking about Little Ice Age moraine dating today. But the yellow one is just to indicate of trying to entice you to my future talks in case if I have those results from southeastern Tibetan Plateau to present in other occasions. So those are the two focus of my study in the past, and it will be in the future years. So I haven't got a chance to go beyond the border of China to in terms of the Tian Shan range. So I'm going to be talking about the Chinese Tian Shan Mountains and the dating within the Tian Shan Mountains mostly today. And this yellow star is indicating the future studies I will do in southeastern Tibetan Plateau. Okay, so the focus of time, for the focus of time period today is going to be on Little Ice Age. So it is a period characterized by a significant cooling of global temperature, primarily affecting the northern hemisphere from approximately the 14th century to the mid-19th century. This era is not really considered a true ice age, but rather a regional cooling phase during the Holocene epoch. The Little Ice Age had profound effects on agriculture, society, and environment during its span. We'll show you a couple of examples of those archaeological evidence. But in the right side figure, you can see during the Little Ice Age, global temperatures were significantly cooler than those of the preceding medieval warm period and the subsequent modern warming period. So although studies have shown that the cooling was not uniform globally, but the average temperature was estimated to be about 1 degree Celsius lower than current average in many parts of the world. This cooling has led to shorter growing seasons. So the starvation in Europe, for example, are well documented and in the written records. And also when it comes to glacier evidence across multiple continents, we saw evidence of expansion of mountain glaciers, for example, in North America and in Europe, including Asia as well. So there are discussions about possible causes of this occurrence of a cooling event, including natural climate variation, volcanic activity, solar activities. I won't dwell too long on this, but here's a couple examples of what has been recorded regarding to this, the most recent cooling period where we see glacier advances. So we know that there are abundant records of the impacts and the timing and all kinds of evidence of the Little Ice Age in Europe, mostly in Europe and North America in US. So, for example, Europe experienced some of the most significant cooling during the period, affecting agricultural output. And this is the painting of the frozen Thames in London in 1677. And here at the bottom is the one of the journal article published about 20 years ago. It was indicating, well, there might be multiple a cool and wet period during the whole Little Ice Age time span. So possibly 3 indicated in this paper by Liu et al. 2003. This is a mountain called Qidan Mountain in northwestern China. And this is speaking to a possibility that we will find twin or triplets of moraine ridges that can be used as evidence for Little Ice Age cooling fluctuations in the region. So the paper really, which delineates the 3 possible stages of Little Ice Age, really didn't provide any chronological data. Here we will be looking at Little Ice Age moraine, like pictured over here. This is from one of my study sites. It's also the well-known sites in the Tian Shan Mountains. So the moraine deposition over here is very striking. So you can tell that oftentimes we are looking for characteristics of those presumed little ice age moraine to be very fresh looking, have very sharp crests. The ridges of the moraine are very apparent. We have boulders deposited on top of it and little to no vegetation cover. And they are about hundreds of meters to a few kilometers away from present day glacier terminus. So those could be the indicator, the characteristics from the landform to say, well, or whether we can assume this is the little ice age moraine. So basically, yes, to just say from the literature that there are not really many evidence, especially chronological evidence, to speak to the timing of the little ice age in this part of the world, high mountain Asia. So the question comes to, we want to determine when is the timing of the deposition of the little ice age moraine, right? So that will be indicating to the time that a glacier reached its maximum during the little ice age cooling period. So the box that we're going to be talking about is within the Tian Shan, especially the Chinese part of the Tian Shan here highlighted in the red box. And then the two methods, the approaches, I want to find out the timing of the moraine is on the cosmogenic nuclide exposure dating, primarily using beryllium-10. And also, since my background coming from master degree and late years of my undergraduate, I got exposed to tree studies. So that's one of the motivations I wanted to study little ice age, is because it overlaps with the ability of the tree ring studies. So other independent age constraints that I refer here is specifically talking about some preliminary results from my dendroval studies that I will show you at the last. So here, this for the part that is highlighted to Chinese Tian Shan, there are climatic studies to say how much of a cooling or wetting this location has experienced. So basically, so if we're looking at Northern Hemisphere, so this is a temperature anomaly during roughly the time where little ice age occurred. And this one is from the Tarim Basin, which is right over here, quite close to our study site. From sediment record, they found clay layer and indicating wet climate during the little ice age period. So the climate change is evident in the region during the little ice age, but we will see what the glacier will say. So the dating method, just briefly, there are multiple variety of methods that could be applied to date little ice age moraine. So speaking of proxy data, proxy material, such as lichens, such as buried wood, such as using weathering rate from rock surfaces, and and then here we can sample exposed rock for cosmogenic. So yeah, I won't explain the individual method that is not involved in the project, but just to speak to the importance of having multiple proxy data that could be enhancing the reliability of our dating results. That's partly due to I'm missing the side of this diagram. This is from Porter, 1969. His work back in time, showing that the glacier advanced in this direction and depositing a moraine, and during the warming period of time, it's going in recession. So different evidence would be indicating different age limits. It's not necessarily always telling us the exact time that moraine is deposited or the cooling event reached its peak. But for example, the tree ring age would be giving would be helpful to identify the minimum age limit for the moraine deposition. And because tree can only grow after the deposition, after the fact that moraine has been deposited. And yeah, so there are possible minimum age limit, possible minimum limiting ages, for example, from the radiocarbon dating of the organic matter in bogs or lakes, or possible maximum limiting ages from overrated or incorporated organic matters from, for example, the buried tree over here. So yeah, so when we interpret those proxy ages, I think we should keep this in mind to say what is exactly the age is speaking to, and what kind of geomorphic processes should be considered. So yeah, so I think the group doesn't need extra explanation on beryllium-10 cosmogenic dating, but just to simply put, this dating method is based on the fact that cosmogenic nuclides are produced predictably over time when minerals became exposed or bombarded by cosmic rays. The rock surface accumulates a certain cosmogenic nuclide at a production rate, which depends on the latitude, longitude, and altitude and depths from the surface, all that factors. And so by measuring the concentration of such nuclide, in this case, it's beryllium-10, and knowing the production rate at a sample site, well, sometimes we don't. We use the calibration sites from other regions. The time of the exposure can be determined for the sample surface. So this is the routine methodology. We collect samples from the field sites and then process them in the lab. This is all back in my early years, being the emergent PhD student, I think. And we did the laboratory work primarily in the prime lab at Purdue University. So yeah, this is Dr. Lee back in the years. Okay, so coming down to the samples, the study sites, the sampling of little ice age moraine in Eastern Tian Shan. Here, this is the Tian Shan, well, the grayish shadowed area in the background is the mountain. And here in the very early days, well, the early study of beryllium-10 dating of Little Ice Age event is from Corpus et al. 2008 in the much broader scale of a study. She, I believe, she produced 2 ages that falls into the Little Ice Age time period. So it's recalculated age to 0.2 and 0.3 Ka. And then for most of my dissertation work a couple of years ago, well, a number of years ago, I have produced new data at these 2 sites. The very first one is called Urumqi River Headwaters. I have 3 glaciers sampled and in a total of 15 samples. This is the site. And then the other site during my dissertation research was this Hasilegan Pass. So there are 3 moraines that sampled in total of 20 samples. And there's like, thanks to Dr. Lee, I'm involved in this international collaboration of Paleoglacier study. So other groups of our collaboration has also produced little ice age moraines across the Chinese Tian Shan area. So the 3 green boxes are speaking to those 3D study sites. So Takala Valley has 3 samples, the Sarenwu Valley has 6 samples, and the Turgan Valley has 11 samples. So those are the samples are particularly dated for Little Ice Age moraines. And then here, the yellow dot, this is the one that I kind of experimented a little bit. I haven't really published anything about this site, but there are 15 marine samples collected in the past field seasons. And also this is the site I have also collected tree data. So I will show you a little bit about the preliminary results for this site at the last. Yeah, so yeah, again, a shout out to the international collaboration team. So the data is kind of covering every parts of at least the Chinese Tian Shan over here. And we can have a better understanding of this most recent event of cooling. Here, the first dating results that I'm going to show you is from the Urumqi River headwaters. So simply I hope the names of the sites don't confuse you, just to be highlighting a few of them. So the two in the red box is the one that I'm going to speak to most. And this one, I think it's worth to note because the Turgan Valley is in the very eastern end of the Tian Shan Mountains. So this is almost close to the border with Mongolia. So that's for the one that's kind of special to remember. But anyway, here, this is the result of the first site. So we'll now call it UG, just the Urumqi Glacier #1 site. And so this two branches was used to be one glacier that was named Urumqi Glacier #1. And this is a long monitored glacier since 1959. And there's a Tian Shan Glaciological Station established at the time and was under continuous constant monitor since then. And I think in early 1990s, the glacier retreated to two branches that we see today. So for this relatively large glacier of UG1, the dating of seven boulders at this site gives a result, a regular camel plot, probability density plot like this. So they are pretty well clustered together. So we are able to use the reduced chi-square test to test if this, we can conclude a weighted mean age out of it. So with the method, we excluded two younger ages and concluded with the mean age of 430 plus minus 110 years for this well deposited and fresh looking moraine at UG1 glacier. This is the one you saw before. And then on the other glacier of UGS, that's S is indicating this is on the southern slope. So on the other side of the mountain. And we had 3 samples and they gave us crazily large ages. So we wouldn't be able to conclude an age out of this. So they're all scattered, very widely scattered. And the UG3, the number 3 here is having the same problems. So the youngest age is about 0.7 Ka, where the largest one ranged to 9.6 Ka. So there are 5 samples in total, but we wouldn't be able to conclude an age out of it. So only one that's concluded to say, well, that deposition of this moraine is formed about 430 years ago. So the second site is the Hasilagan site. So this is the site we have 1, 2, 3 glaciers of various sizes. And for the first one, HDBA, there are 10 samples, but we separated them. When we sample them in the field, we separate them into the inner moraine and the outer moraine. So when we're looking at the data, the dates coming out of those moraines, so the inner moraine gave us a calculated result of 260 plus minus 30 years coming from 3 samples. And then the HDBA outer moraine, if we use the consistent method of reduced chi-squared test, we concluded the age, the mean age, which is the same with the first site, 430 years. Plus minus 40 years here, but this is only from 2 samples. This is definitely arguable to see whether you can conclude an age, claim an age from just 2 samples. And then for HDBB, the second glacier over here, 5 boulders with 1 excluded. The 4 comes to an average age of 280 plus minus 60 years. So this is definitely within little ice age, a very nicely clustered age. And then for the little one here, HDBC, yes, the same problem with the wide scattering, well, all of the 5 not overlapping with one another at all. So these are not conclusive. So that's the data that I have produced for my dissertation by looking at the other 3 sites that also in the Chinese Tian Shan range. And we find similar results for the Takala Valley and Sarenwu Valley. The first one gives the mean age about 270 years, plus minus 20 years. The second one is about the same, 290 years. And the last one, this is the one I asked you, just remember, this is the very eastern end, the very eastern end of the Tian Shan range. So this one has very, kind of the largest to the very earliest time of the beginning of the Little Ice Age, if you say, for 800 years, about 800 years of a time where the deposition of the Little Ice Age moraine occurred. So, well, from those dates, we possibly have seen 3 age clusters across this Chinese Tian Shan range at 750 years, 400, 430-ish years, and then 200, 270, 280-ish years. So there are multiple currents or multiple advances or sub-advances, you would claim, happened during the whole span of the Little Ice Age. So it turns out the 300, 400 year happened most in the central part. Most of the valleys we did it, I'll show you, is in the central part of the Chinese Tian Shan. They're about this age. And then this 800 one only happened for that one particular site in the easternmost Tian Shan range. So even for this very beautiful one of UG1, glacier number 1, we see the separation of the 2 submarines kind of forming a complex. So the one that's outer, giving us in general older ages, and then the inner one is giving about that age that's 200-ish. So for the younger one, I think it's also visible over the site as well. So, but let's revisit the camel plots, because it's interesting that only some of them give us conclusive ages to interpret the landform. And non-ideal cases over here happens quite at quite amount of sites. They are indicating, the assumptions that we make when we take exposure ages is that we assume they have a full shielding from cosmic rays prior to the event, and they are continuously exposed to cosmic rays after the event. So this is the beautiful diagram from Yanan et al. 2011, that famous paper of Too Young or Too Old. So basically, we are looking when we look at those widely scattered ages from the Little Ice Age moraine. Apparently there are quite an amount of prior exposure. The inheritance is quite large for some of the glaciers. So that is the problem, I think, is worth discussing. And then we go back and look at those glaciers that gave us non-Little Ice Age ages, and we kind of figured out. So those thicker ones, for example, the UG1 glacier over here, are quite like bulky, massive in terms of its volume and size. And the one, for example, the UG3 one, it's quite attached to the mountain head wall. It's quite thin. It's not bulky. So in terms of the size or the look of it, the form of it, we argue that apparently those fresh-looking moraines, same kind of looking moraines that we collected sample from, they're not dated to Little Ice Age. The reason for it is probably due to the significant inheritance, the mixing of beryllium-tin signals from the prior exposure of those rocks being originated from the head walls, from the surrounding environments. So basically, we argue that those little thin ones don't possess enough erosional power to produce those freshly deposited, freshly exposed boulders that only accumulates cosmogenic concentrations during the event of Little Ice Age. So that's the argument that we could continue to discuss. But we figured, looking at the glacier characteristics, the size for those who gave little ice ages are quite large, well, larger than the non-little ice age producing glaciers. Are at a gentle slope for this type, and the steep slope for the non-little ice age producing glaciers. So hypsometry is speaking to the one that's giving little ice age results is bulky at the lower elevations, but the one that has non-little ice ages, it's lower mass in the lower elevations. So we can discuss other factors that might be contributing to the geomorphic processes of different types of glaciers. But I think, although they don't give us conclusive ages that we want to look after, but they are still indicating very important geomorphic processes that's behind the glacier itself. So quickly, I think I'm using up my time here, but just quickly to show you the preliminary results of that far away, kind of close to the border site, close to the border of China and Kazakhstan site that I kind of started to experiment. I want to continue on the project to show you the 15 boulder samples have been collected from the Xiaotag Glacier. And so far I've been working with York Schaefer from Colombia to get the results for those beryllium tin dating of the samples. He returned me 7 of them, so we're going to be continuing working on this. I'll show you that 7 results just in the next slide. But also, this is the site I collected 35 tree cores from 35 trees. This is more than 35 cores that I collected. 48 cores I collected from 35 trees. So those trees are producing ages that could be speaking to the deposition of the little ice moraine. So this is the drone. This is the drone image I collected at a site. This is quite massive and complex of a moraine in front of the glacier back to that direction. And you see there's quite an amount of vegetation start to grow at the glacier deposits. And here's the results from the tree ring sampling. And so we were trying to spot where's that oldest tree. And here's the plot. This is work from my master's student a couple years ago. And she produced this plot and found that the germination date of that oldest tree was 1554 AD. And the axis interval was speaking to the time interval between glacial retreat and the first seedling growth. So with this considered, we estimated the one period of glacial retreat during the Little Ice Age was 476 years ago. And there's potentially another one about 213 years ago based on the tree ring data. So then we have to say, well, what is the comparison with the beryllium tin? So although I have 15 in total for the Little Ice Age moraine complex over here, but only 7 have been have been produced with results. So those are the PCAT results I experimented since Storch published the paper in 2022. And if you'd want to say what's the conclusion of the ages, I would well, I think it's still early to conclude an age from it. But if you see the PDE probability density curve, and this one is standing out a little bit, but it's only from like about 2 data points. So I'm waiting for more results coming and see whether we can have a more conclusive age for this and how it compares to that tree ring data. Okay, so more for the next stage of my study, I want to include that southeastern Tibetan Plateau samples have been collected from the sites. And those sites are also going to be, the sites are like very detailed sampled so that we can have a better resolution of the Little Ice Age fluctuation. And also those sites have another independent age controls that we can study and double check, cross check with the beryllium tin data. So this is for my next stage of the Paleoglacier study I want to do. And that will, I hope not using up too much of the time here. thanks for the funding parties, funding agencies, and especially I want to thank for the field helpers and the local ethnic groups, which are Kyrgyz ethnic groups living in the area. And also this work is not going to be possible without the supervision of my PhD advisor, Dr. Lee's great mentorship. So thank you for all, and I hope I can do more in the future couple years. And thank you everybody for listening.
Okay, do we have any questions? I think we kind of run out of time. Okay.
I've got a quick question. Really great talk.
Okay.
This is Dick Hermance, Cal State Northridge. I've got a very similar data set with cosmogenic ages and trees growing on moraines up in the Klamath Mountains. I was curious, how did you come up with the 7-year ascesis interval for your moraines, or for the trees growing on the moraines?
That is a great question. Yes, so we actually didn't track the growth of the tree ourselves. It is coming from a lecture, well, actually from a literature. So this is directly borrowed from another literature speaking to the specific 7 years of axis interval for the same species. And the species I forgot to mention is shrunk spruce. So this is native to the mountain. And a study I believe that my student found that has the axis interval is from Russia somewhere. So about around that same general region. But the good thing is from the same species. But I think, well, it's still doubtful. I mean, 7 years in terms of axis interval, it's very short. It's very short. Yeah. Thanks for asking.
I'm dealing with the same problem, so I may contact you on email, but it does seem short, but it could be right too. So thank you very much.
Thank you. Yeah, definitely.
So you have some question?
Yeah, I'm just wondering, since some of your ages are like, I saw like 20,000 years, like those really old ones. I'm wondering, like, do you know if there's other big glaciation events before the Little Ice Age in the Tian Shan area? Because those ages reminds me of like Alaska for maximum, but I don't know if those events has any footprint in the Tian Shan region.
Yes, definitely. The answer is yes, definitely, for sure. There are older glaciation events recorded by the boulders that we've actually sampled and tested. Yes, definitely. For example, this valley, Dr. Lee had quite a amount of publication around this site that speaks to the older glaciations. But for the ages that's so old at those glaciers, I doubt they are from the older glaciation because the location, right? Because it's right there in front of the mountain glacier. It's more likely they're like tumbled or rolled or fallen from other sides of the mountains, or the head wall sides of the mountain, the other parts of the head wall or headwater areas of the basin. So the older glaciation, the deposit boulders for older glaciations are found in much lower locations, kilometers of lower of a distance down in the valley.
Okay, great. So I think that's almost close our talk. So Ben, do you want to say something?
Yes, I just want to thank our speakers. Thanks everyone for participating today. This is on our schedule, the last seminar, but we do have more to discuss. So watch for a message from me about that in the coming days.
Okay. Anyway, see you guys later. I'm going to stop.
Thank you.
Thank you.